Today I'll be talking about resonance and standing waves. We can force an object to vibrate by adding energy to the object. You can use less energy if you add it at the correct frequency for that object. Many objects have a natural frequency they are designed to vibrate at. So what is a natural frequency? The frequency at which an object requires the least amount of energy to get it to vibrate. And this depends on the shape, the density, the material, and the size of the object. We've all dropped change before, like quarters, nickels, dimes, pennies. They all have a distinct natural frequency they vibrate at, and you can hear that as you drop them. They make different sounds. Can we set an object into motion without touching it directly? Sure, all you have to do is expose it to small amounts of energy at its natural frequency. So some of the demonstrations I'll be showing you in class deal with pendulums, tuning fork boxes, and the Tacoma Narrows Bridge. It's a really interesting video that we'll be talking about in class, how the wind being added to this one little valley got this bridge to start vibrating because it was hitting it at the correct natural frequency. So even a little teeny push added at the correct frequency makes it go higher and higher. And you can see the same thing is true as when you learned how to swing on a swing when you were a kid. You just move your legs back and forth at the correct natural frequency. You don't really have to add much energy, and you go higher and higher and higher. When you do this, resonancy occurs, or resonance, when the frequency of a force vibration matches the natural frequency of the system. And this is like when you're, as I just said, swinging your legs back and forth, adding energy to the system, you and the swing, and you kept it going higher and higher. And here's a little cartoon I found that I thought was a little funny. Kid playing the horn there, and he says, "That's not a note I hit very often." You know, we've all seen the idea of hitting a frequency, either a singer or something, at the correct frequency to get glass to break. And I'll show you some videos of that in class as well. Alright, the fundamental frequency is the lowest frequency of vibration that results in a standing wave. So what is a standing wave? A standing wave pattern is a vibrational pattern created within a medium when the vibrational frequency of the source causes reflected waves from the end of the medium to interfere with the incident waves from the source. This interference occurs in such a manner that specific points along the medium appear to be standing still. And this is a definition I grabbed from this one site, the Physics Classroom. I definitely would recommend you looking at that if you have that one particular website if you have questions. It's a great resource for our class. Commercial's over, and so here we go back. Harmonic series are integral multiples of the fundamental frequency. Now this will all make sense in the next couple slides. So why does a standing wave form? Okay, in reflecting from the wall, a forward traveling half cycle becomes a backward traveling half cycle that's inverted. And this is true because of Newton's third law. The string is pulling up on the wall will pull down on the string, and it will flip. This repeated reinforcement between the newly created and reflected cycles causes a large standing wave to develop. I'll show you an image of that in the next slide. So here's a transverse standing wave on a string. The end's inverted, so let's say it was going this way. This end inverts to form a node. Obviously where it started vibrating is a node. And there must be an antinode between each node. So here's a node where it comes together, and here's an antinode. So between each node, there has to be an antinode. You can see that here. Here's a node, 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 and between each has to be an antinode. So if you look at this fundamental frequency, the first one that forms, it really occurs when it's half of a wavelength. Because if you look at the wave cycle, it goes up, down, and it should continue up again like this. So this is half of a wavelength. So we take the formula for velocity is equal to frequency times wavelength and solve for frequency. We get frequency is equal to velocity over wavelength. And what is a wavelength? Well, it's 2 times this length. So there's where we get this expression, velocity over 2 times this length is a frequency. Okay? And you can see as you keep on going on, you're adding half of a wavelength. Now a little bit more information about the nodes and antinodes. Nodes is where the two waves totally cancel each other out in destructive interference. Well, antinodes are constructive interference, so here's constructive and destructive. And each harmonic you add half a wavelength. So here's the first pattern that forms. The next pattern would just be another like one of these shapes. I like to call them like little footballs. So you have one football, then two, then three. So the velocity doesn't change unless you change the medium. So if you have a wave moving on a string here, unless we change the medium, like by either tightening the string or change the mass period and length of the string, the velocity will remain the same. So with that in mind, as the wavelength goes down, because here's the wavelength will get smaller and smaller as you add a little more humps, the frequency has to go up. Okay? And here's the general format of this. We took our original equation, frequency is equal to velocity over 2L, and we added n in front of it, where n is 1, 2, 3, 4. 1 is the fundamental frequency, or the first harmonic, and then twice that is this one. So you just put a 2 in front of it. So the second harmonic, f of n sub n, f sub 2, would be 2 times the original. And then you have 3, and then 4. And every time you add a half a wavelength, you're adding the next harmonic. So let's try an example. Let's make sure we understand the terminology first, though. In this equation, v is the speed of the sound wave, or of the wave itself. L is the length of the string. N is the harmonic, like the first harmonic, second harmonic, third harmonic. And what you're really doing there is adding those little football shapes. And F is the frequency of vibration. So here's our example. A guitar string that is 50 centimeters long has a fundamental frequency of 440 Hertz. What's the speed of the wave on the string? So we have our equation, and we're going to solve for V. And there we go, we solved it for V. We put the terms in. Okay. And remember that the length has to be in meters. And it comes out to be 440 meters per second. All right, let's try another one. This time we're going to do a standing wave where it's open on both sides. It's a tube that's open on both sides. So the end of it doesn't pinch the sound or the air waves. So an antinode forms. So that happens on both ends because it's open on both ends. But as we stated before, between every node there has to be an antinode, and correspondingly between every antinode there has to be a node. So each of these cone shapes are a quarter of a wavelength. So the simplest standing wave shape are 2/4 of a wavelength, which we all know is a half a wavelength. 2/4 is a half. So the fundamental frequency occurs when this length here, from here to here, is half of a wavelength. So we come up with our same equation we had before. And each harmonic, we add another half of a wavelength. In other words, between each of these here, we put another football shape. So the general format of the equation would be f of n is equal to nv over 2L. We have n's 1, 2, 3, 4, because you're adding another football shape in between each one. And this is for open tube resonators, which once again means open on both sides. And here's an example. You get a person playing the flute. When all the holes are closed on one type of flute, the lowest note it can make is a middle C. if the speed of sound is 343, and the flute is assumed to be a cylinder open at both ends, determine L. So we take our equation. This time we solve for L, and the lowest frequency would be the first one, the first harmonic, or the fundamental, and you can easily see how you solve for L. Alright. Now let's talk about a closed tube resonator. Now a closed tube resonator is open on one end and closed on the other. So the open can't bring it together, so it's an antinote forms. So in other words, it doesn't invert it. Closed, it inverts it. So a node forms. So for the fundamental frequency to occur with a open and closed tube resonator, open on one end, closed on the other, it's only a quarter of a wavelength. Okay? So in other words, what length is this tube? It's only a quarter of a full wavelength. Okay? Alright, so the next harmonic forms when we add another half of a wavelength. In other words, we add another football shape. So here we add another football shape. Here's the original, and we added another half. So we took the original, and we added a half. So that occurs at 3/4 of a wavelength. And then we can add another football shape. We add another half, and then we get 5/4 of a wavelength. And then we add another football, and we get 7/4 of a wavelength. So there's a pattern developing here as well, that f of n is equal to nv over 4L, but now the n's are only the first, the third, the fifth, and the seventh. So only odd harmonics form with closed tubes. And we'll be doing different problems like that. You should really understand the conditions at the end of the tubes and how to draw the shapes and what they look like. And we'll do problems like that in class as well.